anything. I was just talking about the continuous functions.
Well, you have
We
no
can't
bounds.
evaluate improper integrals like this. To evaluate an improper integral, we write that improper integral is a limit of a proper integral. Okay, I'll fix my horrible mistake. I guess what I really meant is this. This is a limit, as maybe, I don't know, I'm making this letter up out of thin air. How about B increase that bound? Of the, nice, proper integral from 0 to B, excuse me, of this mess. I just maintain that now I can anti-differentiate what's in the integrand's position for that proper interval. I think I get this.
Okay.
But I do think, unlike what I had written on the board before, this changes quite a bit. Because I think that's going to give me the following. The limit is B places K. Of this antiderivative evaluated the lower bound of integration. Would that be just this? Minus, did I say lower bound of integration? I meant upper bound of integration, which, by the way, shoot, I am wrong.
Wouldn't
Apologies.
it be -1?
Yeah, I think it would be e to the a minus s to the b.
Yeah, -1.
Minus my 1.
Yeah.
But I think that gives me 1 over a minus s. Well, let's just talk about this limit. This limit clearly goes to
Infinity,
oh, does it?
isn't it?
It depends what A and S.
Depends on what a and s are. I want it to converge. And if I want this to go to 0, then what must the relationship between s and a be?
A must be greater than S.
So say one more time. A is greater than a.
Yeah.
And if s is greater than a, I do think it converges, and I think it specifically converges to this. Or shall I say more concisely, it's 1 over s minus a. In other words, I think Laplace transform evaluated on an exponential function, where I've got e to the as, excuse me, e to the at power, is simply going to be that. Get solved.
You only have half a function now.
What's that?
You only have half a function.
What do you mean half?
What about the part that's listening? What are you going to do then? I don't think this thing is able to use this only half a function.
See, I think the beauty behind this is that for an exponential function of this type right here, I'm only going to be concerned with when a is some number I can deal with, like 5, 7, 20, 1500, maybe. But as long as I just assume my s values are bigger than it, then I've got an easy Laplace transform for it. And think of it, that's just a dummy variable anyways. What difference does it make?
So when you're finding the Laplace transform, are you always trying to look at where the function converges, or why are we looking at that in this case?
Well, I have to. I have no choice. Because if s is not bigger than a, then you have to confess that first term inside the brackets is going to go to infinity. It's going to increase that bound as b increases that bound.
Yeah.
So I am worried about that. You guys, I'm not saying I've given you an example of Laplace transform. I'm not. I'm saying I just Laplace e to the as. Excuse me, I keep misspeaking. I'm saying I've just Laplace e to the at. From now on, you know what it is, because I derived it for you. Could be. I shouldn't be so gender biased. Oh, but you guys, I've got a long list of Laplace transforms to consider. Let's just start the list. Laplace, e to the at. We're simply going to get 1 over.
That's what my mind said. Where s is greater than a.
What would happen if a equals 0? Let's see what happens when we Laplace. You guys, I don't know what I want to Laplace yet. Can I stall for a moment? Because I think my next example is going to be extensive enough. I don't want to insult you by doing what your author does. So can I just take a peek and see what he does? And I'll do the opposite. Wow, he skipped a lot of work. But he skipped a lot of work in producing the Laplace of the cosine function. So let me do the sine function. And if I'm going to Laplace the sine function, something like the sine of bt, here's what I get. The improper integral of e the negative st times the sine of bt, we're going to integrate with respect to t. maintain this is nothing more than, I don't know, how about the limit? As b does the thing again, of this proper integral. What was that?
So, sine of bt.
Thank you very much. I'm just making up whatever's in there. Sine of bt. Oh, you guys, you are Math 31 experts. What's my technique of integration? Parts. Necessarily. And in using integration by parts, I will allow you to be, actually, I don't care what you let me be. How about if it's just that exponential expression? In dv be everything else. I think my du is a piece of cake. But you know what, I think v is a relative piece of cake as well. Isn't that just a, is that going to be a negative 1 over b times the cosine? Bless you, bt. Chris?
Should we change all our b's to a so that we're consistent with the other class?
If you insist.
Just, I don't know.
I have no problem at all. I kind of like changing to B because I was trying to impress upon you that could be anything, but I'll be very happy to be consistent.
Come on, man.
You guys think it works? Well, maybe it doesn't. Shoot, that gives me the limit as k increases without bound of, is that the product of my u and my v, which is negative 1 over a, cosine of at minus the integral of, is that an s over a, e to the negative st, cosine at.
You forgot that first, you forgot u in the first part of that uv.
Wow, I sure did. Is that an e to the negative st? My goodness. Of course, you guys see my whole point behind using integration with parts. I generated another integral that looks just like the previous one, so I'm gonna do it again. And I think my new u is going to be e to the negative st d, period. And my dv is going to be, well, this time it's going to be cosine of 18. But that implies du is a negative 1 over s e to stuff. And v is equal to, is that a positive 1 over a sine of 18?
Wouldn't it just be negative s?
Say that again.
Wouldn't du just be negative s e to the negative s?
Well, if you're to differentiate. Okay, I'll differentiate. Goes integrate. And I think that tells me with the very last integral, you guys, I have the mathematical legal right to rewrite as such. Okay, guys, here I go. I got the product of my new u, my new v. Would that be a 1 over a e to the negative st times sine of 18? Minus the integral of my new v du, but that'll be a positive s over a integral of e to the negative st sine of 18. And I'm going to integrate with respect to t. I suppose my bounds of integration are going to remain such. And you know, technically speaking, guys, I'm still being really sloppy, aren't I? Aren't I really evaluating that from 0 to b? And same with here. Yeah, I really missed that all over the place.
You're missing a closing parenthesis too.
That's right. Oh, you guys haven't changed the k's, I forgot. So Brad, am I missing a set of parentheses?
Closing parenthesis after the sine of at dt.
Because all of that's being affected by the s over a. Now, I think this is going to give me, in the end, the limit as k increases without bound of, is that a negative 1 over a cosine of at minus an s over a squared sine of at, all of which is being multiplied by the exponential factor, and evaluated from 0 to k. You guys so far so good.
So,
I
one of
think-
the integrals is missing the bounds.
What's that?
One of the integrals is missing the bounds.
Oh, you're right, this one up here? So that really should be 0 to k, shouldn't it? Thank you. You guys did something wrong with what I have written. I'm missing the entire last term. I'll put it back in. And if I evaluate the limit all at the same time, doesn't that give me a minus s squared over a squared times the improper integral from 0 on up of my e to negative st sine of a t? Did you guys see it?
Yeah.
That being the case, to actually answer my question, which is what the heck's Laplace in this thing? Then notice how this thing right here really is nothing more than minus s squared over a squared times the Laplace of the sine of at. So putting on the left-hand side of the equal sign, Laplace of s of at, then the sine of at, excuse me, then I can actually add that term to both sides of the equal sign. And I think if I do that, I'm running out of room, you guys. I'm going to jump over here. If I were to do that, add s squared over a squared times the Laplace to both sides of the equation, I think it gives me this. Being equal to darn limits that you see on the right-hand side of the equal sign with the first term. That's this. Minus this. Times this.
Missing parentheses.
I am. So what do you guys think you could say about the evaluation of this limit?
Wait, there is no k. Where's the k? Oh, k gets replaced with t. I got it.
Yeah, so if I actually evaluate this at k, then what can you say about k increasing or bound? What's the first term going to do?
Approach 1.
I can't.
Approach 0.
I think it's going to go to 0. Minus this evaluation at the lower bound of integration, which is 0, but that just becomes a 1. And so what did I end up getting?
Approaches 0 in the second term.
I'm sorry I'm so slow, you guys.
Yeah.
The sign of 0 is 0.
Negative 1 over
The
a.
cosine of 0 is 1. And so am I not just going to end up generating a positive 1? Unless you,
Wouldn't it be negative 1 over a?
well, careful, that's lower bound integration. I'm subtracting this
Oh,
at the lower bound
yeah.
integration. I'm skipping a few steps, sorry. Oh, but that means the Laplace of the sine of at is nothing more than, get a little bit of cancellation. I guess I'm left with a over s squared plus a squared. That's the Laplace of the sine function.
Black magic.
Is it really? I think it's beautiful.
I was, for some reason, I don't know how I stumbled upon this, but I was reading a webcomic about Laplace, and somebody knocked on the door. I can't remember who. Some famous actor knocked on the door. He went in, and Laplace had gone crazy because the devil manifested his soul because he had sold his soul to the devil to find this out.
I like that. Well, then, you guys, if you don't mind, I'm not going to go through the very, very similar process to show you that the Laplace of the cosine of at is actually equal to s over s squared plus a squared.
Question.
Yes, sir.
Because the Laplace transform is linear, what you have written with the Laplace transform of 1 is also applicable to
So in other words, Laplace of C is just equal to C over S. Because the C's get pulled out of the Laplace transform, it's a linear transformation. See how clunky that would be? If you guys didn't have an understanding of linear algebra? In a DE class, I just have to say, believe me, it's just a property of integrals. It just doesn't sound smooth.
How much of differential equations can you really teach about law?
I just think, again, the language for me, certain things I can't justify as smoothly. But you know what? Most universities do teach these classes completely separate. One's not a prerequisite for the other. So you guys, let me come through and show you an entire list. Guys, I'm a little nervous. I think this is the best text I found out there for combining linear algebra and PE. But I confess I'm a little disappointed that at the end of section 1, I don't know, section 1 or 2, I think section number 2, that he gives entire lists and most of it is unjustified. And so he talks about these shifting theorems, whatever the heck they are, but never mentioned previously. But I do think it's fair for me to say this. I've derived this one out then. I didn't derive this one. I did not derive that one, but it's very similar, and he shows it in the book. But he skips a lot of steps. Here's something I haven't shown. But this is easily justifiable with what you know about having t to the n power in the integrand position. Just it would work very easily. You just apply repeatedly integration by parts.
I'm sorry, can you repeat that?
Yeah, I'm just saying, to justify that the Laplace of t to the n is equal to this, you're simply replacing the f of t with t to the n in the integrand's position. You can apply integration by parts repeatedly. Shoot, you guys, you know what? This is a statement involving n factorial. Will be another really nice way of proving that Laplace of this is equal to n. Mathematical induction would be beautiful. I think when it comes to these two, please don't look at them yet. Here too, he doesn't discuss what these really represent. Besides that, they're intimately related to the shifting theorems anyways. I'll get to it when the time comes. Chris?
So what do you do if you have t to the n where n is its negative integer? Do you give up?
That's a good question. I don't know. You know what? By definition, the corresponding improper integral diverges. And so in that case, I'd have to say that I don't have a Laplace transform for that particular function. Not every function is going to have a Laplace transform because I define a Laplace transform in terms of an improper integral, and not all improper integrals converge. If it diverges, I don't have a corresponding Laplace.
So it works with t to the n.
Yeah, that is one case now.
How does the pi get in there?
You know, I don't know. Can we look at it?
So does the book walk you through the steps of how to derive each and every one of these, or?
No, and when it does, it skips a lot of steps. That's why I'm going to go through a couple of really important ones today, like sines and cosines, exponentials.
Then just consult Patrick JMT for the rest of them?
But you guys, I can't do this in my head. Can you just take a peek at it real quick? Oh, come on, what did I do with my pen? So, if I were to Laplace t to the negative 1 half, by definition, here's what I generate. Or shall I say correspondingly this?
Yeah, you can't take advantage of the circularity of the trigonometric function.
No, you sure can't.
So,
Turn into a power series.
I was about to say that. You can substitute some power series in for a SE. That'll only take 3 days.
I don't see any other way. I don't think you can do it without a power series. Yeah, I don't see any other way. I think it has to be. Interesting, how do you do it though? So Bradley, now coming into place, maybe he doesn't actually show this.
Check Wolfram Alpha. They often will do a step-by-step on some of these.
But I just want to see if he justifies it. Okay, guys, I'm done. He doesn't. That's why I'm suggesting that with a lot of these that he generates, he doesn't actually justify his steps. However, this is a list with which you and I will be familiar. I just don't care about the one with t to the negative half.
So, this list of Laplace transforms, do we need to memorize this, or will this be something that you would provide us with on a test?
Oh, you'll know them by heart.
Okay.
You'll know everything on the list except for this item right here. But everything else, you know.
It's either this or annihilators, Professor.
Yeah,
Only do one.
and then we got all those axioms too that we need to memorize.
Oh, no, you don't memorize those.
Oh
You already
yes,
know
we
them.
need to know and understand that.
Well, you know, you guys, I did not plan this today. I got time. Can I spend 10 minutes giving you the very first step of really getting close to solving these Laplace transforms?
Okay.
And since I got 10 minutes, what this means is the following. Tomorrow when I come to class, I'll be able to solve DEs, period. We'll be able to use these to solve differential equations. It is so slick. But I gotta admit, there's one really important tool missing, and that's this. It's a bit of an abstract sign. But if I were to Laplace the derivative of some function y, and I don't know what the function is, I think by definition, here's what I get. The improper interval of my y prime at t, e to the negative st, dt. Excuse me. And I think that that is equivalent to the limit as k plays its game of 0 to k. Same darn stuff in integration. It's just that with a tad bit of integration by parts, only one application. If I allow u to be e to the negative st dt, and dv be equal to y prime, this means that du is going to be negative 1 over s, e to the negative st, but it means v is going to be equal to, I agree. Oh, did I forget my dt? I'll put it in.
Shouldn't just be negative s for du. Yeah, it's a German.
My goodness. I'm just a mess all over the place. I don't need my dt there, and then yet again, I'm yet again integrating, I should be differentiating. Wouldn't that be this? And in applying my integration by parts formula, I suppose I can rewrite that definite interval in the following fashion. It's simply going to be the product of my VU. Minus the integral involving my VBU, which is going to be a positive s, times y e to the negative st. That's gonna give me the following. I think I've got, is that the limit? As K plays its game. You guys, I'm gonna put in a couple steps at once. Tell me if I'm doing too much. Evaluating this beast at the upper bound of integration gives me this. Minus this expression evaluated at the lower bound of integration, but that's simply gonna give me this. And I maintain that when I take a peek at the next integral, you guys, I don't think I'd want to do this. I got an idea. Let me bring the limit back in. Let me pull the s out. Isn't that just simply the integral from 0 to here? Or shall I say, in evaluating this limit, I think this whole first term drops out. And I think all I'm really left with is s times, well, look at that, that's just Laplace of y minus y divided by 0. That is really slick. You guys, can you look ahead, play a little chess? If I Laplace both sides of maybe just a first order linear differential equation, then I think Laplacing y prime, I can translate it into Laplace of y, and I can treat that as an algebraic math D equation to isolate Laplace of y in that equation. And that is exactly what we're going to do. Might require some partial fraction decomposition all over the place, but it's certainly something I can handle. Something else different about this technique. Notice I've got a y0 there. In other words, Laplace transforms is a technique to use when you have initial value conditions. So now we're talking about serious applications where I do know something about the original function. So everybody, I'm afraid this is something I definitely need to add to my list. So now I realize Laplace, the derivative of some function y, is simply going to give me s times Laplace of the original function y minus my function divided by 0. Can you guys imagine what's going to happen here? Anybody? S times Laplace of y prime minus y prime is 0. Oh, but wait, hold on. Laplace of y prime can also be interpreted as whoops, hold it. That meant to be a brace. But that must imply the Laplace y double prime. I get s squared Laplace of y minus s times y of 0. Minus y prime of 0, that's yet another thing I can add to my list over there. Now you can see that even with a second order d, when I plot both sides, I can transform everything left hand side in terms of Laplace of y. Give it a name to it, call it y. And again, it's a math D question. So can I just hold off on solving PEs till tomorrow? And for those of you who want to practice,
Oh, and we didn't get homework last week, so
thank you. On what section?
on the big one, the
I'm so
7-6.
sorry,
Yeah.
you guys.
So are we finished with 7?
You know, I'll come back to
tonight,
there's
or-
some odds and ends towards the end of the
Okay.
semester. So
Can you,
7-6.
Can you maybe tell us which which sections we're not going to cover through the rest, just in case I want to try and push ahead a little bit in some of my spare time.
All right.
All right.
So in 7-6, just look at 1 through 7. Well, you should add 8 to that. In section 7-7, can you take a peek at the following? Number 9. 10. Gee, that's not much.
This is the
9 and 10, the
Applications.
applications. I'll try to create some more.
9 and 10? All right.
And for tomorrow, can you take a peek at the following? Section 8.1. One through 7 on. Fourteen, 15, 16. Nineteen, 21. Oh, he did it. Number 37, so beautiful. 37. I'm not assigning this, but number 38, he does derive through the exercise Laplace t to the negative 1/2. And he does not use power series.
I just put that there anyways.
Very cool. You guys, that's a lot. So it's basically going to take a little time to get caught up.
Oh, and can you maybe tell us
Oh,
which
yeah.
chapters we're not?
You guys write down if you want to go. So Brad, can I tell you the section I'm definitely going to cover?
Okay.
And then I'm going to come back when I have time to pick up whatever I can. So you ready?
Yeah.
Much different.
Thank you very much.
Oh, yeah,
So
I've
different.
also got a block as well.
All of chapter 8,
All of chapter 8?
skipping that one.
Okay.
It's a lot nicer to have your own mark.
I've been working on homework.
Going around.
Yes.
Very good one.
Yes, I usually have my own too, but
Cause I live
I haven't been that regular about it lately.
Oh, that's.
9192.
Oh, yeah, I got your email.
Just no ifs, ands, or buts.
Alright. Type it up as if it's like it looks a lot like the book.
9.4.
Yeah, I just use math.
Okay.
Then I'm going to pick and
Alright.
choose.
I'll get to mine,
We should do diagonalization,
hopefully by
Oh,
the
yeah,
end
that's
of the
because that's really what I wanted to see. All right.
Just as long as it's not like the bottom.
Okay.
You take it back.